All right. Give this a second to initialize. Make sure I get people on here. So, first of all, bear with me. I'm working on 2 computers, 3 screens, and an iPad. I can show you the setup I got working right here. Turn the laptop around. So I got the desktop going. I got my iPad there. So if I'm looking around and doing weird stuff, that's just because I've got a bunch of stuff going on to try to make this thing as useful as possible. So I understand that you guys don't necessarily have your laptops. So you may not have all the stuff and the link or whatever. This will be posted to YouTube, so I will send you guys the links. If you have questions, let me jump over here real quick. You can, so while we're talking, if you're here, you can post questions over on the right-hand side. There should be a bar there to type questions in, and I will answer those as we go. I only have questions from 4 people, so this will be a fairly short video. So I guess we might as well get going. Let's see here. First question was from, a couple questions was from Frankie, talking about the notes that were posted. Frankie was asking about the statements that says the total amount of energy in the universe stays the same. His question was, he's aware that the universe is expanding, which it is. And his question was, what's happening to that energy? If the total energy is constant, but the universe is expanding, shouldn't the energy per unit area be decreasing? And if you guys think back to chemistry last year with Piasecki, you remember entropy. You know, the total amount of disorder is always increasing. Things are getting more and more evenly spread out. And so this is going to be something we talk a lot more about in option D when we do astrophysics. But the short answer for now is yes. The universe is expanding. The total amount of energy in the universe is constant, total energy. But right now it's kind of localized. You know, you got your stars and your nebula and your stuff like that. And so the energy in space is being spread out, and we will go way more in depth with this in option D. So for now, just kind of table that question. Oh, before we go, one thing I meant to say. Some of the things that you're seeing in here are first introduced in other topics. So we jumped ahead. A lot of the nuclear stuff, when we talk about nuclear power plants, will make more sense after we talk about topic 7. Some of the electricity stuff will make more sense after topic 5. So if you're a little fuzzy on some of the stuff that's going on, don't freak out. It will get better as we go through those topics. It'll be much more clear toward the end of our time in IB physics. That being said, moving on to Frankie's next question. His question was about specific energy. I'm going to jump over to the textbook, and this should show up on your screen. Oh, where's the textbook? Should be there. All right, hold on. Let's try this again. There it is. So, looking at this page in the textbook, Frankie's question was, does this apply, does every source, does every fuel source have a different specific energy? The answer is yes. And this table right here is the one that specifically talks about that. You see there in the middle column right here that, let's see if I can highlight that. Crude oil has a specific energy of 46 megajoules per kilogram. Vegetable oil is 42. Diesel's 46. Sugar is 17. Cow dung is 15. So yes, everything does have a different specific energy. An important thing to note is the difference between specific energy and energy density. Specific energy is megajoules per kilogram. Energy density is megajoules per liter. So specific energy is talking about mass, and energy density is talking about volume. Those are important things to be aware of, especially if you come across anything from the old curriculum. Be careful, because the old curriculum did not talk about specific energy, but what they did talk about was energy density, but they used it in the context of specific energy. If that sounds confusing, don't worry about it. That's why I tell you not to look at the old curriculum. So just make sure that you're clear on the differences between specific energy and energy density. And every fuel source has its own specific energy. Just like when we're talking about specific heat, every material has its own specific heat. Let me jump back to here. So next question was about centrifuging, when you're enriching nuclear fuel. His question was simply, what is centrifuging? To make it simple, basically you spin stuff around really fast. They do it with blood a lot. You can separate the red blood cells from the white blood cells from the plasma. And so basically just take your test tube of blood, spin it around really fast, and the more dense stuff is heavier, so it ends up on the outside. Your less dense stuff is lighter, obviously, and it ends up on the inside. And so you can separate things by their density, by their masses. Same thing happens with uranium. Most of the uranium is useless. It is uranium-235, which is not, why am I getting that backward? 238. Most of it's 238, which is not radioactive. A very small percentage is uranium-235, which is the good stuff that you want for your nuclear reactors or nuclear weapons, but that's a different story. And so you get a bunch of extremely well-balanced metal drums, put your uranium ore in there. The reality is a little more complicated. And you just basically spin it around really fast. And what happens is your heavier uranium-238 ends up on the outside wall of the container, and your somewhat lighter uranium-235 migrates toward the inside of the container. And so you basically strip out the uranium-235, and it's not going to be pure, it's just going to be a slightly higher percentage. So you strip out that higher percentage uranium-235, put it in a new centrifuge, and keep spinning it over and over again until you reach that critical density that you need to sustain nuclear fission. We can get a lot more specific. We're going to take time when we get back to school to go over this stuff a little more specifically. Jonathan, I see your question popped up. I will answer that a little bit later. So that's what centrifuging is. Frankie's next question was about pumped storage, talking about taking water, pumping it to a reservoir somewhere to use later, which in my opinion is what we need in the state of California. We need more of it. His question was, can droughts affect pumped storage? The answer is, of course, yes. If you have less water available, you are not going to be able to pump it to a reservoir to use later. So yes, droughts definitely will affect pump storage. The argument in favor of more storage of water is that when we have non-drought times, you could be storing more of it to be able to draw on during a drought. So that's that one. Frankie's final question was regarding an image on the notes. Let me pull it up real quick. This is going to be a really ghetto way of showing you what his question was, but it will work. It was on this picture here. His question was, where are the fuel rods? Because there's nothing on there labeled fuel rods. The fuel rods will be these red things here labeled fissile material. So the red rods are the fuel rods in this image. And so that is where your uranium pellets would be. And I think that takes care of Frankie's questions. Next questions were from Emily. Emily had a couple questions about energy in general. Her first question was, why is only some energy useful, and what happens to the energy that is wasted? When we're talking about power generation and stuff like that, we need electricity we need energy to do something. We take energy and fuel. Looking at that table from earlier, you've got coal or natural gas or anything like that. There's energy contained in that, and we want to use that to generally generate electricity. Is what we want. And so when you are extracting energy from coal, you burn it. When you extract energy from natural gas, you burn it. When you extract energy from nuclear fuel, you are basically allowing the natural radioactive process to generate a whole bunch of heat, harnessing that heat, and then using that to spin a generator, which then generates electricity. And so really, all of those things, whether you're burning coal, burning natural gas, or using nuclear, your whole point is to boil water. If you looked at the diagrams in the book, let's see, what page would that be on? Let me jump back over to the book real quick. If you look at the power plant diagrams, zoom out. So you got coal-fired here. You've got nuclear there. And I think gas should be on this next page, or did I skip gas somehow? Anyhow, the main goal of all power plants is really to boil water. And if I can zoom in on this image, all you're doing is you're boiling water to be able to spin this steam turbine. And so, can I not draw on here? So anyhow, this turbine here is a steam turbine. And it doesn't matter if you have a coal plant and a natural gas plant or a nuclear plant. You are just boiling water to spin a steam turbine, which is basically like think about a pinwheel, where the wind blows on it and makes it spin. And so that spins a generator, and that's what creates electricity. The only thing that changes is where you are getting the energy from. And so that's going to be your nuclear, your coal, or your natural gas. And so every time you change energy, we talked about this a little bit in topic 2. Anytime you change the form of energy, it's inefficient. You're always going to lose stuff. And so the main way we lose energy is by heat. And so if you look at the Sankey diagrams here, you've got, when you burn the coal, you've got heat lost. When you have the thermal energy in the steam, when you turn steam into mechanical energy in the turbine, you are losing heat. When the turbine is spinning and then the turbine in turn spins the generator, you are losing energy to friction, which again is heat. And so every step of the way you're losing stuff is heat. And it can be, to answer her second question, energy can be transformed into many types of energy at once. Best example is what you guys were probably seeing a lot of on the 4th of July, and the 3rd of July, and the 2nd of July, and then last night on the 9th of July. Fireworks, right? You light a firework and it goes boom. And so you have sound, you have pressure. If it's a really big firework, you can sometimes feel the pressure in your chest from the shock wave. You obviously have light. You've got heat, and so you get all those things that happen at once. So yes, to answer Emily's second question, energy can be transformed into many types of energy all at once. And then Emily's final question about energy was, how can energy be transferred from one type to another? Does it depend on the situation? The answer is yes. Basically, you are the type of energy that you are looking for will determine what you do with your initial energy source. Say you're trying to get a car to move. You take the energy contained in the gasoline, you burn it, which creates a whole bunch of heat and a whole bunch of pressure from the explosion. That spins your engine, which pushes your car down the road. If you are trying to heat your house, you take wood or pellets or natural gas or whatever. You can even use electricity, and you use that to generate heat to heat up your house. And so the type of energy that you are harvesting depends on your goals. And so if you're trying to make a car move, or if you're trying to generate electricity, or if you're trying to generate heat, cook food on a stove, something like that. It all depends on what you're trying to do. And so I hope that answers any of those questions. Next questions. I see Jonathan was asking a question about what I was talking about. So yes, Jonathan's question there is water. Why can't I see this? There we go. So Jonathan's question, is water always the main source to make electricity, or can there be another type of liquid in order to conduct electricity? The water's not conducting electricity. You are taking the heat from the burning of whatever, or from the heat from the nuclear reaction, and you're taking that heat to boil the water. And so then you go from liquid water to high pressure steam, which has a lot of energy. You use that energy to spin your turbine. Okay. Water is the most commonly used. That's really the only one that you're responsible for when you take the test. All right, moving on to Gabby's questions now. Gabby had two. Her first one, do we need to know the advantages and disadvantages of different types of energy sources for the test? The answer is yes. You need to know the advantages and disadvantages of wind power, advantages and disadvantages of coal power, of hydroelectric power, of nuclear power. So yeah, the main things that are discussed in the textbook, you should have at least some idea of the advantages and disadvantages of those different types of electricity generation. You don't need to separate coal and natural gas. You can just lump those into fossil fuels. They have the same advantages and disadvantages. So you can go from there. And her second question was, is uranium the only element we'll be focusing on in this topic? Because of the nuclear stuff, uranium is really the only thing we're going to be talking about as far as periodic table stuff. We might mention plutonium when we talk about what are called breeder reactors for nuclear power. But yeah, uranium is the nuclear fuel. It is naturally occurring. You can really just go out into the desert in Arizona and Utah with a metal detector and a Geiger counter, and you can find uranium ore. It's going to be pretty much perfectly safe because it is, just barely radioactive. That uranium-235 is an extremely small percentage of what that is, but you can go out and you can collect radioactive ore. It's a naturally occurring element. It is the heaviest and largest naturally occurring element. If you look at the periodic table, everything larger than uranium is man-made. It is created in a laboratory by humans. Everything from hydrogen all the way up to uranium on the periodic table are naturally occurring. And we will get deeper into that in option D as well, as far as how they are made, which is really cool. They're all created in the cores of stars, which is fun. But more on that later. That's it for Gabby's questions. Next up is David. He had 3 of them. The first one was talking about the 8.1.1 worksheet. So let me pull that up real quick so we can take a look at it. Right there. He was asking about question number 2 here. He was asking specifically about part C, asking about, does the specific heat capacity of water play a role in heat? And the answer is yes. You're told here, so a coal-powered power station produces 440 megawatts of electrical power, has an overall efficiency of 31%. Part A and part B, no big deal. Part C, the thermal energy that is lost at the power station is removed by water taken from a nearby river, which is true. This is the way things work. It's the way they're done. The water is then fed back into the river and must not be more than 5 degrees Celsius hotter than when it was taken out. Calculate the rate at which the water must flow through the power station. And so this is where you do have to use the topic 3 stuff, Q equals MC delta T. Let me see if I can do what I want to do here. I want to look at this. Yes. I get to use my fancy little drawing tablet. So if you look at number 2, just kind of a very brief intro to part A. You have to do more of this for part A, but for now, this is good enough. If you've got 440 megawatts of useful energy and the efficiency is 31%, you run that through our efficiency formula, and you end up with 1,420 megawatts produced total. And if 440 of those are useful, that means that 980 of those are wasted as heat. That's the heat that we are getting rid of in the river. And so part C, you are going to have to go with the Q equals MC delta T. Okay, Q is going to be your 980 megawatts. And remember, that's megawatts. You've got to get out of megawatts. Okay, you got to go back to watts. I'm not going to tell you how to do that. You should know, and you do. Your delta T, it says that it must not be hotter than 5 degrees warmer than where it came in. So your delta T is 5 degrees Celsius. Your C is for water, so it's 4180. And then you are solving for M. Okay. The question asked you, what is the flow rate, right? So you're talking about a watt. Remember that watts is a joule per second. And then you get the mass of water. Water has a density of 1. So density is mass over volume. So it has a density of 1. You get the mass. You can get the volume, and that'll give you the what you're looking for that question. So you can go ahead and use that. I was intentionally vague because I want you to work your way through it, but hopefully that will give you enough start to hopefully work your way through it. All right. David's second question was about hydroelectric generation. So in hydroelectric generation, is energy lost to friction between the water and the front of the water column? For our purposes, no. In reality, yes, there is friction, there's turbulence, there's what's called cavitation, where the water's moving around and all kinds of weird stuff happens. But for our purposes in IB physics, just assume that there are no frictional losses, excuse me, when water is going down the hydroelectric pathway, okay? And David's final question before I get to Kayla and Jonathan's questions here on the side, do we need to know the diagrams of the power stations? No. Should you be familiar with them? Yes. So just looking at, this diagram here, do you need to be able to produce that? No. Should you have a basic understanding of how this thing works? Yes. Okay, so that's our coal-fired I thought we had. I thought they showed national units. Yes. Nuclear is here on this page. And so same basic idea. You've got your fuel rods here are the little tiny black lines. The big black lines are the control rods. You've got your graphite moderator, which we'll talk more about when we get back to school. And then basically this light blue stuff here in the chamber is what gets heated up. That gets transferred via the heat exchanger, so there's no direct contact with the outside world of the nasty radioactive stuff inside, which again, you got the high pressure steam, turns the turbine, turns the generator, makes electricity. You take that steam, you condense it back down into water, run it back through so that it boils, turns into steam, and you just go from there. So you should have a basic idea of how these things work, but you will not be asked to reproduce any of those diagrams, okay? Back over. All right. So Jonathan, question here. Can you explain the figure 8.7? Also, what does the S and N stand for? Let's go take a look back at the textbook. Find figure 8.7. It would have been nice if you provided me with a page number, but I think we can find it because that's 8.9. Moving backward, that's 8.7. Okay. Oh, this will make a lot more sense after we talk about topic 5. This is the basic setup for for an electrical generator or an electric motor. That little thing in the middle with the S and the N, that is a magnet. The S is the south pole of the magnet. The N is the north pole of the magnet. If you are using energy to spin that, it's a generator and it generates electricity. So that's how it would work in a power station. You would have that high pressure steam turning that turbine. That turbine shaft is connected to the rotor, is what that thing in the middle is called. That rotates and that creates the flow of electricity in that loop of wire. If you take that motor and do it the other way, if you put electricity through that loop of wire, it will force that magnet to spin, and that's an electric motor. So anytime you have an electric motor turning something, that's exactly how that works. We will talk a lot more about this in topic 5, so don't worry about it too much now. In the caption over there, it says use Fleming's right-hand rule to give the direction of the current. We will specifically talk about that in topic 5, so don't worry about that now. Good question, though. Thank you for asking, Jonathan. Kayla's question here. Does hydroelectric specific energy only apply to water? Yes, hydroelectric by definition is water. And so you are using water to generate electricity. So that, yes, that only deals with water. And that's, the whole thing about water falling downhill. So yes. Kayla's next question. Is there an equation that we need to use in order to find specific energy? No real equation, it's just a principle. It is the energy in joules per kilogram of a material. And so if you say we've got 1,000 kilograms of coal being burned and we generate 1 gigajoule of energy. And you got 1 gigajoule over, which a giga is like 10 to the, whatever, it's like 10 to the 12th, it's in your data booklet. So you get 10 to the 12th over 1,000 kilograms, that would give you your energy density, I'm sorry, your specific energy for that fuel. Mr. Freeman, last question posted on here, we're gonna have a short session. Are there any major differences we need to know when it comes to specific energy and specific density? This I briefly talked about earlier. I'll jump back to the textbook and we will look back at this page here. And so the main difference, Nick, is that specific energy is in megajoules per kilogram and energy density is in megajoules per liter. And so again, specific energy deals with mass, energy per unit mass. Energy density deals with energy per unit volume. So it is a little bit different. And one thing that they don't show on this table, which is really unfortunate, you're showing all these different things: diesel, gasoline, vegetable oil, crude oil, sugar, wood. When you look at uranium, specifically uranium-235, the specific energy of uranium-235 is in the millions of megajoules per kilogram. So if we look at diesel fuel, gasoline is pretty close to diesel fuel. Diesel fuel here is 46. It's the third one down, middle column, 46 megajoules per kilogram. So you take a kilogram of diesel fuel and burn it, you get 46 megajoules of energy out. You take a kilogram of uranium and you let it do its radioactive thing, which we'll talk more about in topic 7, you will get millions and millions of megajoules out of that 1 kilogram of uranium. So that's one big benefit to that. Kayla's got another question for us. Would we need to use the equations we learned in topic 3 in order to solve question 1A, or just the worksheet in general? The answer is maybe. I'm not going to give you that, but if we go look at the worksheet again, zoom out a little bit. If you're talking about temperature changes and stuff like that, then yes, just like I did the example for David's question, you will need to use Q equals MC delta T at times. Same thing with the efficiency calculations. If you're given efficiencies, if you're given efficiencies, you will need to use the efficiency equation. So yes, there are some, the weird thing about topic 8 is there's very little unique stuff to just this topic. It kind of uses stuff from other units in the context of this energy generation stuff. So yes, the stuff that we've already done does come back, okay? So yeah, be aware of that. All the thing that IB loves, we've talked about it before, they love, wait for it, synthesis, right? Taking stuff from one topic, moving it into another topic, and being able to use those two things together. They love that. And when we start doing our test review in the spring, you'll see how that works, okay? So that's that. Edwin, will specific energy have any relation back to specific heat? I don't know. I've never thought about that. If it does, cool. If not, yeah, something you can investigate if you want. As far as I know, it does not, because specific heat is talking about the temperature change when you add energy to a material, right? How, you add energy to it, how much is the temperature change? Specific energy is talking about the energy released from a chemical reaction. So if you take that material and you break it down to its chemical constituents, what are you going to get out? So I don't think they're going to be necessarily related there. All right, good question. Frankie, why is electricity a secondary source when it is involved in most energy production? Oh, this one here, this has been asked before and I can't remember. I had a good answer last year. Primary sources of energy are things, oh, I got it. Primary sources are what you get energy from. And so electricity does not just exist. You can't just go outside and dig up electricity. So that means it has to be produced, which is why it's a secondary source. Primary sources are things that you can find in the environment. So coal, natural gas, uranium. Uranium's kind of a fuzzy one because it needs to be refined. So uranium ore is primary, but the uranium that we use in the nuclear power plants and nuclear weapons has to be refined, so that would be a secondary source. And so primary sources are things that you can find directly. A secondary source is something that you produce with that primary source. So I hope that helps. And looking at my screen, unless somebody slaps a question up there in the next couple of seconds, I think I am going to be signing off. 36 minutes. Only 6 people here viewing. No worries. I think it probably has a lot to do with the fact that lots of people don't have their laptops or whatever. I got emails from several people saying that they're not going to be able to watch live, but they'll look at it later. Just in closing, this will be automatically linked to YouTube. If you go to the Google Hangout page, let me jump over there real quick. Should be right here. So if you go to this page here, where you went to log into this thing, over here links, you click on links. You get 3 options. You got the event page, which is this website here where you're at, and the YouTube page, which is where this YouTube video will be linked. And so I'll post it on ManageBack as well. So if you want to go back and listen to me talk again for 35 minutes later, you can go do that. It is a private video, so searching for the title of this Google Hangout is not going to bring anything up. But if you have that link, you can do that. Oh, Frankie, you had to go ask another question. Darn you. Why are there 2 different types of Sankey diagrams in the notes, and does it matter? I'm not exactly sure what you're saying, so let me pull up the notes. Oh, you're talking, if you're asking about, some of them are just like lines that are drawn. Okay, I think I see what you're asking. All right, I'll pull the notes up on this computer. So I can put it on the screen, stand by. All right. And so Frankie, I think, is referring to like that kind of diagram where they're just arrows. That's technically not a Sankey diagram. That's just a quick just drawing of where the energy goes. This would be a Sankey diagram. But what IB likes to see are the ones that look like this, where the heat comes out the bottom. All right. So I probably should go clean up those diagrams in the notes. That's actually a really good question. IB likes these, where the heat dumps out the bottom. Even this one is not an official IB Sankey diagram. When I was building the notes, I had to go and just get what's in the internet. When you're looking at Sankey diagrams and looking at this one is just just a crazy diagram I want to show you. But when you're looking at this stuff, use the ones in the textbook. So use the ones that all have the wasted energy coming out the bottom. Okay, let me jump back to the textbook. So the textbook is consistent. Just it takes a long time to actually build these in the notes, which is why I didn't do it. So when you're talking about Sankey diagrams, this is the format you want to use, where the wasted energy coming out as heat comes out the bottom, and the useful energy progresses from left to right as that main area. So this is the format you want to follow when you're making Sankey diagrams. And remember that the thickness of the arrow is proportional to the amount of energy going on. So when you've got this little heat loss on the left, this big fat heat loss in the middle, The big fat heat loss is a greater amount of heat loss than the little tiny arrow. So just kind of keep that in mind. All right. Thank you for asking that, Frankie, and I apologize if there was a confusion about that. Thank you for the question again, Frankie. Is all fission controlled, or is there uncontrolled fission? If you have a nuclear power plant, you are really, really, really hoping that the fission is going to be controlled. If it's controlled, you can control the amount of heat that comes out. If you lose control of the reaction, you get too much heat and the containment vessel melts and you get what's called a nuclear meltdown, which is basically the nuclear fission just keeps going and going and going and going. The most common form of uncontrolled fission is a nuclear bomb. In a nuclear bomb, you've got your uranium-235. You set off a special explosion to compress that 235, and that creates enough energy to get them to start splitting apart. As they start to split, and we're going to go way more into this in topic 7, but as they start to split, they give off more neutrons. Those neutrons create a chain reaction, and you get essentially all of your uranium undergoing fission within a fraction of a second, which is why nuclear bombs are so freaking terrifying and powerful, because it is an uncontrolled fission reaction. So to finish that off, in a power plant, it is controlled. Yeah, you are controlling the reaction based on the size and shape of the fuel pellets, and also with the control rods moving up and down between the fuel rods. In a nuclear bomb, it is just ready, set, fission, and lots of energy released at once. Mr. Freeman, if thermal energy is usually what's transferred in energy degradation, does that mean that most energy in the universe is thermal? This gets into option D again. Eventually, yes. Okay. There's something called cosmology, which is the study of the origin and the eventual fate of our universe. And, where do we come from? How is it going? What's gonna be the eventual outcome of the universe? And in cosmology, they've pretty much figured out that at some point the universe will all be the same temperature. Right now we've got these stars. Stars are born, they live, they die. Their death gives rise to new stars, and yada yada yada. Eventually, there's going to be not enough mass and energy in one place to build more stars. Everything will cool off, and then the entire universe will be a uniform temperature, and I think they've estimated at about 5 Kelvin. The temperature of space right now is about 3 Kelvin. So it is not, space is not absolute zero. There is some residual heat there, and that's evidence of the Big Bang. And we'll get deeper into that in option D when we do astrophysics. But so right now, most of the energy in the universe is nuclear, because all stars are giant nuclear reactors. Not fission, though, nuclear fusion, which is the opposite reaction. Where fission, you have a big thing that splits into 2 small things. With fusion, you have 2 small things that are smashed together and fused into one larger thing. And we'll get way deeper into this in topic 7, but that is the fuel source for all stars. Okay, so thank you, Nick. Frankie, are we ever going to take a look at sound energy? Yes, we will. That is topic 4. We start talking about waves. Sound is a type of energy, and it is a type of wave, and we'll deal with that in topic 4. I know there's a little bit of a lag between when I talk and when things broadcast to you, so I will wait about 30 seconds for any other questions to pop up, and otherwise, thank you 6 for being here live. Oh, now we have 7 viewers. Thank you guys for being here. Thank you for those of you that submitted your notes. Thank you. I did make an assignment in ManageBack, so you can go drop it in that Dropbox on the assignment. Some people have emailed me. Some people have texted me. That's fine. as long as I have evidence of your notes. And due to the computer distribution issues, I'll give you guys a couple more days. So those of you that have not submitted your notes, get them done and get them submitted, please. Olivia, are we going to have a test on the first day back, or will we have a review day? Olivia, we will have a review week, probably. Going through the notes, going through any other questions that weren't answered here, going through the problem sheets, looking at some more review stuff. The practice exercises at the back of the chapter we'll go through. So we will not have a test the first day. It'll probably be sometime during the second week of school. Okay, thank you for asking. Right? If I didn't mention that before, thank you for asking. Every time I give you guys 30 seconds, you'll throw another question. So I'll give it some time. One last chance. Again, I hope you guys are having a great summer. We're about a third of the way through. So we will see each other again at the next one. When is that next one? August sometime. August 7th. So I apologize for the confusion. Thank you for those of you that made it over to this Hangout. I was just trying to make sure everything was set up right, and I accidentally clicked broadcast, and I screwed up that thing. So on August 7th, same place, same time. You're welcome, Olivia. Frankie, what exactly do solar heating panels do? They heat stuff. Forgive the sarcasm, but solar heating panels are what are used to heat pools. And so if you look up on people's roofs, usually there's kind of a big tube thing and then like a thin black panel. You pump water through that. The panel's black. It absorbs a whole bunch of energy. The energy is transferred to the water, and you basically heat up your pool at just the cost of running a pump to pump that water, instead of having to actually run a heater to heat the water yourself. And that's something that we will definitely talk about when we get back, because that's a huge source of confusion. They sound similar, right? You talk about solar panel and solar heating panel. What we refer to as a solar panel is better referred to as a photovoltaic cell. Photo talking about photons, which is light. Voltaic is electricity, volts. So photovoltaic makes electricity. Solar heating panels just take the heat from the sun and transfer it directly into the heat and usually water. You can actually hook up those types of things to your water heater and get a little bit of a heating boost from the sun for your water heater, stuff like that. But yeah, so solar heating panels just collect heat. Photovoltaic panels are the ones that take sunlight and change it into electricity. So thank you, Frankie. And I'm going to do a countdown, and I'm going to click off because I'm tired of talking to you. So if nothing else pops up, as always, feel free to email me. Feel free to text me. I got a couple texts in the last couple of days. So please feel free. I may not answer right away, but I will answer. With that, thank you all for being here. I hope you're having a great summer. Enjoy the rest of your summer, and I will see you on the first day of school. Couch, you're out.